So, welcome everyone. I'm excited to kind of just dive a bit into one of the very interesting topics that I will actually encounter almost every day, which is a topic on search and and how the big one of the biggest e-commerce, Amazon, um, has built a solution around efficient efficient search system, which is Rose, and we'll talk about what exactly it does and like deep dive into it a bit as we go. But yeah, it's something that has very interesting um, implementation details, and we'll go into all of that. But before, of course, going into the details of it, we first need to kind of introduction, kind of give an introductory information around Amazon product search. I hope everyone knows about it, but like a quick introduction. Like I think with Amazon search, as you can kind of imagine, you search for an item on the search bar, and it needs to provide that particular item, right? I think it's pretty standard, obvious thing that a search engine should be providing or a search system. But going beyond that, the product itself is an e-commerce where you would want to kind of get the things that you're wanting for, like buying. You want to buy something, you need to be able to use that and be able to retrieve that product so that you can buy it, right? But with search has, of course, with product search anywhere, there are challenges with search engines in general in terms of latency requirements, the scalability aspects, the amount of data being ingested, the amount of queries being processed, all of it. It's essentially a computer science problem, and it still is. There are a lot of new innovations being happening in search even at the moment. So it's a very interesting domain. And I myself work as a search system in one of the marketplace systems similar to Amazon, but on an experience-based marketplace system, which is Get Your Guide. So I do have some bits of experience with annoying search systems, honestly. We'll go into the details of Amazon product search, and then how they've implemented an interesting search system that is essentially a cache for commonly occurring queries. So caches basically are utilized in search systems to enhance user experience. Right? Like we want to make the queries faster and also maintain high quality of results. Right? Like this is very important. Like if I search for a laptop and I get an iPad, the results, that doesn't make sense. I mean, it does in some places, but more often than not, you want your top results to be laptops. So this is kind of caching is kind of achieved by frequently accessed data, store them, right, as normal as caching goes. But with search is interesting, and we'll go into details of how caching is a bit more complicated than a normal caching system in general. But in terms of product, like latency, why caching is because latency is important. So latency has an inverse correlation with conversion rate. Like this is kind of a well-proven across marketplaces, not just like Amazon, but like as I said, Get Your Guide as well as other marketplaces, Temu, whatever. So it has an inverse correlation with the conversion rate and a kind of a direct correlation with bounce rate. So people just bounce, they don't find the correct search results or like accurate search results, which is, of course, it's annoying. Like I think anyone and someone who works on search systems, as I said, I get a lot of flack for messing up search whenever we do that. But yeah, the use case over here is in a scale more than what I work on, honestly, every day. But it's very important to understand like overall search systems kind of behave similarly across the domains. And search traffic kind of escalates, the size of cache increases. So how would we maintain these kind of cache, right? Because like I said, latency is important. So for that latency aspect, I kind of create a cache, but that cache doesn't work in cases of a legacy system, which is search, because the queries can be random, right? Like it can have Nike shoes, and I'll kind of, by the way, before that, I'll also kind of take some examples during the presentation and kind of follow through those examples more often. It might be repetitive sometimes, but yeah, just bear with me on that. But yeah, Nike shoes and Nike shoe sounds similar, but your caching system might just not cache both of, like, won't consider them the same. So you will have a cache miss rate, which is higher in this case, right? But before even jumping into the cache system and all that, just kind of introduction. Rows is the cache system that we're going to talk about. It's designed to handle misspellings, typos, as I mentioned, while also maintaining the efficacy or recall of the search results, right? And our implementation of it is super interesting, which is where we actually will talk about. It uses a randomized hashing schema to kind of manage a large set of different set of queries, and that randomization leverages some interesting algorithm that we'll talk about. But yeah, the challenges are essentially making sure that cache is fast. It's memory constrained as well, because of course there's no infinite memory. So you need to kind of make sure that it's memory efficient as well. And rows basically is. So moving on, as I said, like with modern product search engines, like we do have machine learning models, right? Like they're in fact really, really effective in terms of recall. Like when we type for query, and if it goes to a machine learning model, which is trained with the huge amounts of data, and kind of the training set and the feature set is defined accurately, like it works amazingly well. 95%, 98% of the efficacy that it provides with a query. However, of course, as I mentioned, search systems are notorious in terms of kind of having real-time latency being fast, right? Like the latency should be low. I mean, so with ML models, like there are, of course, relevancy matching, and then you kind of also have to go into ranking, right? Which is another layer of search, which kind of also gets hidden from the complexity, but it's quite important. Ranking is one of the most important things of search system. Then there is a query annotation models that kind of you would enrich your queries to correct the queries in general, right? Like kind of show like how Google search does it, or if you kind of have misspelling or something, it would just correct it for you. There are also algorithms, query string algorithms, as well as ML models. And ML models fundamentally are more often than not, and again, just it's more of an empirical value, but they are CPU bound, right? So they are compute intensive. CPU is not cheap if you want to scale ML models. So yeah, and with queries, like you can get with Amazon, there would be just, I would say, 10, 50, 80, 100,000 queries per second. I don't know. I think honestly, it's going to be super huge amount of traffic. So yeah, ML models great, but doesn't work fully well with the search systems, modern requirements of the search system, right? Like, which is user just put bounds of if the queries is slow or API is slow. So that's where we of course need caching, right? Like I think caching is where more often than not it is super complicated, but then with search it gets even worse in terms of complication, right? With query search or lexical based search. So usually one key issue that hurts the quality of search is that there's like presence of low performing queries, right? Which are queries where even the search engine kind of fails to return high quality and results. So if the cache itself is also low performing, you would kind of have problems with the conversion. And analysis show that most of these failed cases are due to the typographical errors, right? So as I said, like typos, no results from the search engine. Let's say you don't have the most sophisticated ML model to kind of convert it to more semantically matching query, but it would still no results. You would just end up annoying the customer, honestly. So low performing queries and with caching, it becomes, as I said, more complicated. Queries are usually the performing or the tail end of the queries. Long tail queries are usually they do match semantically, right? But again, they have typos, they have some something that is kind of uncommon with the common occurring queries. So if you could map these low-performing queries to the semantically high-performing queries, because they would potentially match, um, it would be nice. So with this, when with caching mechanism, if you do it, then it's also the recall is better as well as it's fast. So yeah, best of both worlds, right? Like honestly, it's going to be a miracle if we have this perfect system, but it's not, of course, and we'll go into details of why. But we could on Amazon shows that we could reach in a kind of a good middle ground where it works really well. And so yeah, for cache, we want to kind of also have low miss rate, because then the whole point of cache is to kind of provide faster response times. And if you have higher miss rates, it means more often than not you are, if it's more than 50%, more often than not you are actually just not using the cache effectively. So introduction more to rows, this is basically the tag that I'm talking about, but kind of rows, or like how they have defined the system in Amazon, is that it's kind of a solution to overcome the challenges faced by traditional caching for query or lexical-based systems. Right? It significantly enhances both speed by reducing the response times and accuracy by improving the search quality. And we'll go into why search quality comes into play over here, but it's an interesting way to implement it. This dual improvement is crucial for maintaining a kind of competitive edge, of course, in this product space overall, e-commerce, right? And Rose has good also operational excellence and designed to effectively manage large-scale data, right? That's the most operational heavy work is queries and caching queries, and thinking about the traffic for a query. You can just imagine how much the size increases each day with different set of product offerings that Amazon offers, right? So kind of on the technical side, Rose is rooted in its kind of use of advanced algorithmic techniques that it uses. It uses like a locality sensitive hashing to ensure, which is abbreviated as LSH, to ensure that the cache data remains relevant over time, and the integration of like reservoir sampling. The second kind of technical aspect of the Rose is that it allows to kind of sample the data, kind of selectively sample it, so that you have a low memory footprint when you kind of deploy the system. And then of course there's another kind of the aspect of better results, which is count-based case. Go into details of each and every aspect of the technical aspects of the system. But just like a spoiler alert kind of a thing. Based on the paper, it seems like Amazon, after deploying Rose, it has showed significant improvements in the system and business metrics, which they've already kind of given as a spoiler initially in the paper. And that's when we actually go and are more interested in reading about it, because it's a positive impact for the business. And we'll discuss more in details of locality-sensitive hashing, reservoir sampling, and count-based case selection, and why they're kind of very interesting and how they implement. So Rose architecture is kind of it's simple. It's broken down into two big components, two major components, which is index generation component and then real-time retrieval or online retrieval component, right? So it's the offline generation of the index itself, which cache uses that in memory. Excuse me. All of this, by the way, in memory. They haven't really mentioned anything about using disk-based data structures or anything like that. So it's mostly memory-based data structures in memory-based data, and that's why also, as another aspect that I mentioned, the sampling mechanism is really important in this aspect, so that the memory footprint is low. And then of course, online retrieval is the real time. Whenever there's a query during query time, you would that is a component that makes sure that the results are appropriate for the query, and they match an existing query, or they correct the typo, all of it. But before moving into like the component itself, it's important to kind of understand some concepts, as I mentioned earlier, which is one of the first important concepts is LSH. So just kind of an introduction to LSH, and then we'll deep dive a bit more as well. But so locality, it's basically locality sensitive hashing. It's a very interesting technique that allows us to kind of effectively and efficiently perform similarity searches in high dimensional spaces. Um, it's not a semantic model it uses, or like a machine learning model. It's a it's a hashing based technique that it uses to kind of convert vector spaces to lower, like high dimensional vector spaces to low dimensional vector spaces. Low dimensional spaces that kind of moves into a hash bucket um, um, representation of a hash bucket, right? So the core idea of LSH is to kind of hash data points in such a way that the similar items are much more likely to be in the same bucket or hash to the same bucket. So the hash value, like in simple terms, the hash function, let's say one single hash function that you have, if Nike shoe and shoes are the two queries in that hash function, they should, again, should in double quotes, but in a very simpler terms, should be producing same hash, right? So that the bucket that they are in, the list of matching for this is the same, because Nike shoe and Nike shoes mean the same, right? So like just a simple kind of a real world example is that if imagine you're like a large in a party with many guests, and instead of introducing yourself to every single person, you would kind of find those who share your interests, like a categorization of people, right? Like if you are a tech person or a finance person, you would group yourself to more towards a tech person, or in case of finance, being in finance, you would group towards finance. So that's more or less like a bucketing technique. Won't go into too much detail of the real world example. It's simple grouping mechanism or clustering mechanism, right? And this is where the LSH algorithm works really well. And in terms of machine learning, especially with the rise of and this is used by the way quite heavily across multiple systems, LSH does play a very important role in vector database. There are databases that use LSH to index the embeddings efficiently, like for sparse search and fast approximate searches as well. For instance, a music streaming service might use LSH to recommend songs so that they can kind of hash the song features into buckets, so service can kind of quickly find and recommend a song similar to what the user likes, right? Without having to compare every song in the database. That's low. So sorry, yeah. So just kind of a quick note on this. LSH has probability hashing, right? So it's not deterministic. Important to note again. But yeah. So deep diving into LSH, I think it uses one of the properties of random projection, and so the hashing phase essentially there is broken down into three main parts, which is hashing, binning is bucketing, hashing is generating the hash value so that it's similar, and then the querying is kind of efficiently locate the value, right? But the hashing is where the statistical aspect comes into play, and it uses random projections or randomization of vector, and then you have a dot product with that random vector. Again, won't go into too much details. You can kind of read about random projection as well if you want to kind of deep dive a bit more. But it's more of a mathematical technique to kind of reduce the dimensionality of set of points in a Euclidean space, and random projection preserves the distances well enough to be similar. So between vectors, or by vectors, I mean like of course bunch of floating points that you determine for a query, right? But the empirical results are sparse. So kind of they have been applied to many natural language tasks under the name random indexing. So that's the technique that random projection random indexing uses, which is random projection. And binning is basically organizing the hash codes into bins and buckets, like group data points based hash codes into buckets, significantly reducing the search space for similarity searches. And of course, querying is when you do query, you also need to hash, because you kind of convert that particular query into hash. And do the bucket lookup, candidate gathering, which is another aspect of ranking that we'll come towards. And then, of course, refining the values. So you kind of pick the top value and all of it, or pick that truly similar values, and not like. So when you search for a dishwasher, it doesn't just give you as a first result is what it's not the best. But yeah, just probably a bad example, but yeah, just an example. So before again moving into a bit more into the rows system, because I think that's where we have parked for now. We are kind of understanding the fundamentals of randomized projections and why it's so important in this case, and like how does it kind of relate or not so much relate to PCA or principal component analysis, where principal component analysis is also used to reduce the dimensionality of the vector space, right? And kind of capturing the most important features out of those vector space. But conceptually, random projection differs from PCA in a very simple way. PCA calculates the vector or direction that maximizes like only the true of the variance of the feature. Variance of the features between the features would be the outcome of PCA, and remove the ones that don't vary as much. So there's no loss of information. Versus random projection, it just simply picks any vector and then performs the projection. So there is a loss of information over there, right? So PCA is more lossless versus random projection is lossy. But the simplicity of randomized projection is where it shines. It's super simple. It's computationally less intensive than PCA, and preserves the distance well enough for the most of the use cases that we want to talk about with Amazon Product Search, and for caching, basically, right? And also, like in terms of memory footprint, it has lower memory footprint as well than PCA. But yeah, this was in terms of computational aspect of both of the approaches I was talking about, but this is more of a statistical or mathematical mathematical definitions of both of them. And you can read about them on the slides. But I'm moving on to LSH itself. LSH is kind of uses random projections, right? And HNSW is also another aspect of approximate nearest neighbor search. So LSH is something that we use for approximate nearest neighbor search, as well as HNSW is more of an algorithm, or an algorithm graph-based algorithm that allows to also do similar approximate nearest neighbor search. But again, the differences are similar as previously mentioned. PCA and randomized projection is that LSH is lossy, and kind of converts it and bins it into an hash value in a very low dimensional space, and probably in just a one single scalar value as well. Versus HNSW preserves all of that, or IVF flat. You can kind of look into any approximate nearest neighbor algorithm. So the comparison can be done, but again, it depends on the use case of how your dimensionality of the data looks like, and what is the outcome that you would want with your similarity search, right? And if you kind of worry about recall more often, and it don't require to be as fast as LSH, then you can use more sophisticated ENN algorithms like HNSW, right? But LSH does work really well and scale well to a point, but after some at a level, it does not scale as it does not scale, and it's not as better. In fact, HNSW is better than scalability aspect and LSH after some point. So yeah, and also IVF flat and similar kind of similar buckets of approximate nearest neighbor search. Um, Now going back to the main topic, which is rows and how rows leverages LSH, right? There are again multiple aspects of LSH and how rows uses them, which is first of all there are like three major aspects, which is signature generation, hashing strategies, and reservoir sampling. And as I mentioned, to manage memory, reservoir sampling is important, but we won't go too much details of it. I will just go quickly into the signature generation. And primary goal of the is to create a unique identifier for each query that captures its similarity to the query, right? As simple as that. Using LSH rows generates the signature based on specific similarity measures, and we'll go into what are the hashing algorithms is. But for example, two queries with similar wording or related product types will have similar signatures. And hashing strategies over here, there are two major important hashing strategies that they have mentioned that they use. One is lexical preserving hashing, which is to ensure that the queries with similar lexical structure, more or less, as I mentioned, Nike shoes and Nike shoe into the same bucket because they match lexically much more closely. And this lexical content of the query to generate the hash code. Versus there's another aspect of marketplace-based search, which is the type of the category of the product itself that's being searched for. In this case, we, as an Amazon, leverages product type preserving hashing, which is to group similar related same products into similar type, like red Nike shoes and blue Nike shoes are essentially Nike shoes, right? So the product type in the end is going to be shoes, and then there is layers of weight and all of it. So this part uses entity recognition as one of the primary implementation name and recognition to kind of produce this particular hash value, and we'll go into details about how they do it. And the reservoir sampling is to map the memory footprint, essentially, as I mentioned. When working with queries in large volumes of data, there is process kind of a stream of data and then from a sample of size R from the large data set of size M. So basically, you can kind of see the parameters that I mentioned on the slides. This ensures that the memory remains constant, right, throughout the life cycle of the cache system altogether. So it doesn't go beyond. And the key parameters, as I mentioned, L is number of hash tables. Again, the hash tables concept is important here because there will be not just one hash table when the query goes, but there will be multiple hash tables so that each aspect of the query is taken care by different types of hashing. And then, of course, there are multiple hash algorithms, right? Which in this particular case, from Amazon's point of view, they have used three hash algorithms, but basically these are the different types of different types of techniques, different types of parameters that to define specific for the specific use case. And M is, as I mentioned, the volume of the data or the data size itself. So since LSH is like randomized procedure, Amazon does one interesting thing about it is that they boost the probability of hashing similar queries together by maintaining L-independent hash tables for the index, right? And this independent is very important. And the work kind of focus on two hashing strategies, as I mentioned, lexical preserve hashing and product type hashing. Under the hashing framework, the size of the hash tables kind of increase linearly with the volume of data, and hence it's required to kind of reduce it by user uniform sampling. And then we'll go into details about like how the online retrieval works with a similar kind of setup, right? So when the query kind of is received, rows performs again the cache lookup to retrieve the most relevant results for this particular query, right? So let's walk through like steps quickly. Query processing first, the computation of LS's signature is done, which is, as I mentioned, the signature value. And signature captures the similarity of the query to other cached queries. And then the signature is used to kind of look up the corresponding bucket in the hash tables. This step kind of helps narrow down to the only those queries that are likely to be similar. And then after that, the relevant bucket is found. This is where the aspect of ranking comes into play. The need to rank the cache queries, the queries that match basically, and then they need to be ranked. So if the hash value for 10 hash tables, or let's say 2 hash tables, and you have two queries in the first hash table that match and 1 query in the second hash table that match, then now you need to kind of rank these collision values in how many times the queries collided, right? So for example, if the first hash table has Nike, so let's say your query is Nike shoes, and the first hash table has Nike shoes, Nike shoe, and Puma shoes as the match, and the second hash table has Nike shoe, then the Nike shoe has the Nike shoe query, the one that is not the main query, the user query, but in the cache. That Nike shoe query will be will have a higher rank order, right? Because it's collided twice than Puma shoe. So the results of that Nike shoe needs to be ranked higher than Puma shoe and the other queries that match. If they don't, we ignore it. So I'll just quickly show one example that you can. It's in just a rough documentation. I'm trying to kind of show this, but so as I said, like Nike running shoes with 3 hash tables, and then if let's say there is a collision with Nike sneakers, like let's say the hash matches Nike sneakers, and Puma running shoes and Nike shoes, there's a 1 collision with each, 0 collision elsewhere. Then the aggregation happens where the Nike sneakers have total, and this aggregates across all the hash tables as 1 collision. Others have 0 collision, or like Puma running shoes has 1 collision, Nike shoes have 1 collision, and now the rank happens accordingly. So Nike sneakers is the first, Puma is second, Nike shoes is third. Right. And there is no order specific thing over here. It's just whichever is being picked first. So it's more random over here. But yeah, so this just kind of gives more detail about the account-based system for ranking. So yes, so by using this count-based case selection, the online kind of retrieval process runs in constant time, by the way, which makes it really efficient. The efficacy of this is crucial for maintaining the performance of the product search, which typically have strict latency budgets, as we kind of are aware of. And yeah, moving on, we would now go into a bit detail the types of hashing or types of hash algorithm, right? Because that's what we kind of spoke about. And one of the first hash methods is lexical preserving hash, which across the queries, you would want to kind of match similar queries in bucket or have a same hash altogether, right? So that's the whole point. This is very interesting, and there's a lot of theoretical underpinnings around this aspect. And again, go through the paper because there are more citations than I can go through within the scope of this particular presentation. But there are like 5 to 6 people being cited for how the signature or this particular hashing technique works. But we'll just go quickly. And so this first of all, the queries are represented in a form of S of Q, as you can see over here. And this is basically in a simpler terms, just kind of a merge or union of unigrams, bigrams, and trigrams. And they've kept 3 as like the max value or the trigram value because empirically it worked really well based on like experimentation. And these combination along with the words combination is kind of a set. It's basically a set, right? And this set along with a different set, let's say, so I need to go into an example again. Let's say I think I should have added it here, but let's say we have Nike shoes and Nike shoe, and we convert that to this particular set. Just convert Nike shoes into this particular set. We want to make sure that's similar to the another set of unigrams, bigrams, and trigrams, which is Nike shoes, right? So this is where the checkout similarity uh, value comes into play, or the formula comes into play, where we want to make sure that this value is high for these particular two queries, right? And but we cannot do it for against all the queries when the query is being received, when the new query is received, or during indexing time as well. So this is where a very interesting hash algorithm comes into play, or hash signature algorithm comes into play, which is min hash. And it uses like a kind of an approach called densified one permutation hashing, which allows single query value to maintain this checkout similarity eventually, right? So if this checkout similarity is, let's say, normalized value is 1 or 0.8 or some 80% or something between two values, the min hash value that it performs and the value of min hash for the other query that has this match will always have 80% similarity. So this is where this, and they will always match. I mean, so the checkout similarity is maintained across the data set. Right? And yeah, through this as well, it's an interesting algorithm and approach. And the second type of hashing is product type preserving hashing. This is where I said entity recognition models are used, or entity recognition approaches are used. So this is like shoes, dishwasher, detergent, laptops, like all of these aspects of a query are weighted. I mean, when using this particular thing, because if higher the weight, the higher the chances that they match similar, they produce similar hash as the one with same type of product, right? So, NER model is used to extract this product type, and then the tokens are weighted. So again, it's a token set of S, like again, as I mentioned, the bigrams, trigrams, and unigrams, as well as the word values, tokens, and then assigning the weight to the tokens. If token is a product type token, like determined after the NER, then the weight is assigned greater than 1, whereas the other types are kind of 1. But in real world, Amazon found out that 10 was an optimal weight for product type. And then again, to maintain checkout similarity, it computes weighted min hash signatures, similar to what we saw before. But in this place, it uses weighted min hash instead of min hash, but it's basically it assigns weights to the values, generates hash values for each particular element. And then there's of course, the weights is more of probability distribution. So kind of the element that is chosen proportional to the weight. And the compute signatures uses like the hash values to compute the min hash signatures that eventually is going to be the same as similar product types. Right. Yes, so that's pretty much it for this particular hashing. And okay, so after all of this is more of a theoretical underpinnings of the algorithm complexity that and Rose's complexity, overall time and memory complexity. But during indexing, the average time complexity of computing the hash is for one query is of LT, L being the number of repetitions or hash tables, right? And LSH, and then T is the average number of tokens per query. The complexity of getting the entire cache structure, this is the indexing time, by the way, is of we go of L and T for n queries, right? So just multiply by basically. But it's again important to note here that this is fast because L and T are small constants. It's much less than n. So we can consider like the time complexity be linear to the number of queries, honestly, which is amazing, to kind of generate the index, by the way. For retrieval, it's more of a polynomial time, where again the retrieval step is number of hash tables into the average number of tokens, and p is the so and then you kind of multiply it with the p and t value. B is basically an hyperparameter value that is also constant, and it's a kind of bucket size that you would define for each hash table, because then you have to go through each bucket values as well. So in practice, again, L, B, and T are small constants. So as a result, the cache retrieval time complexity is more or less constant, right? So this is it's also amazingly fast, which means it is basically behaving like a normal cache, but for a lexical use case. So yeah, and memory complexity, you can see the memory usage is not increasing the size of cache. This enables rows to kind of achieve fast retrieval speeds. There is also analysis of errors being done, so that due to randomized nature of LSH, it is kind of important to kind of identify that if the amount of times the query is mapped to an unrelated bucket or unrelated like that's no similarity bucket, then that's an error, right? So it's still there's still probability over there. So we just basically it says that it needs to be kind of measure it, and then what Amazon did is kind of dramatically reduce this particular error probability by maintaining independent hash tables. As I mentioned earlier, it's the independence of the hash tables is really important to kind of determine each feature set more appropriately. And this error, and in particularly they have applied kind of standard Chernoff bound arguments, which again there's a more citation that you can read through to conclude that the error with the independent hash tables is really low, and it exponentially decreases with as function of L. So it's inverse relation with the function of L, or the number of hash tables basically. This is more of the results of the experiments, the offline experiments, and won't go into too much details, but basically it's a data set of containing 60 million values, well-performing queries, and they have kind of distributed in buckets of normal queries, hard queries, normal being the top percentile of frequency, hard being lower, and long tail being really, really low tail and tail frequent queries. And for each set, there are kind of 1,000 randomly selected queries, and the design of experiment looks like that two key questions were evaluated. One is assessing the accuracy of the rows retrieval process, and the second is efficiency of efficiency, or evaluating the efficiency of rows indexing and retrieval. So basically the time, right? So each methods are tested with rows with lexical preserver hashing and with product type hashing, exact match cache, like it's compared to exact match cache, and standard hash map, basically brute force. So running across all the queries and kind of brute forcing through, and then embedding vectors using Flash. So it's like more of a, as I said, HNSW, or like maybe approximate nearest neighbor, or maybe exact nearest neighbor match. But yeah, so and then this kind of is compared against each, and you can see the results. Pretty good results for rows. Rows outperforms other methods across all datasets, which is amazing. And then the relative performance gain of 1.2% in recall and 2.2% in F1 over best baseline, which is again like that's one of the more interesting results I see over here, which is which I didn't expect when reading through the paper initially. And then the speed improvements, as it's a cache, and more, in fact, it's constant time retrieval. One of them, the values over here is 65 minutes for index generation for LP, like lexical hashing, and for PT 75 minutes of index generation. Uh, so it's definitely impressive. But for retrieval, it's like 2 milliseconds of online retrieval versus 120 milliseconds for files. So yeah, go through the data set. I think honestly, going through each of them doesn't really help much when I speak about it. Just read through it and read through the paper because it's one of the very interesting results that I've seen. Um, and then they kind of use rows for different use cases, and they use for query rewrites. And the metrics you can see, production impact in Amazon search was positive as well. Click-through rate increased by 7%, while um, the bounce the defects rate, reduced by around 2%, as you can see, or 1.5%. So not too bad. That is the results. And they use it for query rewrites as of the results, and for product time annotation, they also evaluate it based on the amount of the queries that they get to identify or annotate the products. And you will read this is to make sure that so some products have special pages, right? Like, or the landing pages with a different type of component and how it's designed. Like this is more of from the UX point of view. So a shoe brand, Nike itself, would have some partnership with Amazon, and the query now needs to understand whether it's Nike, right? So this annotation really helps in this case. Rows really helps in this case, that it is able to identify that's Nike, and now Amazon can redirect the query or the user to a Nike-based special page that they have partnership with to provide some discounts, some etc. So this allows for Amazon to have a much broader reach in terms of for the customer, so they can kind of get what they intend, and in fact far beyond that, right? So the rows kind of reduce defect rate by 1.7%, as I mentioned earlier, which is significant improvement. And yeah, it also identifies like defect rate. So if on the results page, you can see the first value without product type restriction that is not used, is not leveraging rows. It still shows for a dishwasher, it still shows some detergent, but after employing the product type restriction, it is better, right? Like in general, it doesn't show. It's more related, but it doesn't show those values in top values as well. So that's important. So spoken quite a bit already, but in conclusion, Rose overall is quite a bit of a robust cache, and has maps known online query to cache queries by preserving the query intent via lexical and semantically. And the proposed model is definitely highly scalable and deals with hundreds of millions of queries in general in constant time and constant memory, which is amazing, and incredible outcomes over here. And this paper also produces like theoretical analysis of rows, kind of just to understand how it is. So you just don't need to use similar in case you want to build something similar. Cannot just go. You don't need to use the same structure as they have done, but employ more of the concepts, because that was the whole point of the presentation, is to understand the concepts behind how this incredible system comes into play. And then you can kind of build your own system like this using those concepts, and even going beyond with the citations, and kind of trying to kind of figure out best for the use case that you are trying to build for. And yeah, that's pretty much it. Any questions? I've been speaking a lot, so I'll just allow if anyone has any questions, and then let me know if you want to reach offline, or reach me, like get the particular slides or more information around this as well from me. Just message me on LinkedIn. You can find LinkedIn on this particular. Uh, I'll give you the link in the chat. But that's me. That's any questions? Just let me. Um, So I think with rows, it's more the paper doesn't really kind of expose like how they do most of these search engine stuff. But with rows, what they do is they don't use it directly as like a results layer, as I mentioned in the last, based on what the paper says, but they more use it more of enriching the query to then leverage that information to provide better results. Uh, so again, if you go through the paper, you kind of see that they haven't really kind of given an impression whether rows is like a direct um, layer of it doesn't replace the search engine as a whole, but enhances the query in a way that allows the search engine to work much more effectively. So that's where I would say briefly I would assume that based on some filters, it would still go to the search engine with the filters, but the query is now annotated with more or better information to um, to provide better results in case, right? Um, but yeah, feel free to just go through and read it. And I do see they have clearly not explicitly mentioned how they use it, but the last two main points are kind of suggesting that they don't directly use it as a more of a cache for each query, but they use it to annotate the query in near real time, which is again a feat of engineering work. Any other questions? If not, we can of course get going, and yeah, enjoy the rest of your day. Thank you so much for joining and listening to me. Thank you so much, and bye. Enjoy.